So today's lab is on nucleophilic substitution reactions. And a nucleophilic substitution reaction is a reaction which a electron-rich nucleophile donates electron density to an electron-deficient electrophile, and in the process, they form a bond. Here is an example of one type of substitution reaction. This is an SN1 reaction. And as we can see here, it is a two-step process. In the first step, the leaving group takes its electrons and leaves, forming a carbocation intermediate. This intermediate gets attacked by our nucleophile, which donates a pair of electrons to it, and they form a bond in the process. Now, the solvents that promote SN1 reactions are polar protic solvents because they stabilize the carbocation intermediate. The best substrates for SN1 reactions are tertiary carbon substrates, followed by a secondary, followed by a primary. This is because tertiary substrates form the most stable carbocation, which is a tertiary carbocation. Now, there's an exception that you'll see in this lab. We will have an allylic alkyl halide, and these do form primary carbocations, but because they have resonance structures, they're stabilized through resonance, so they're more stable than they seem. Now, the other type of substitution reaction is known as an SN2 reaction. This is a one-step process where the nucleophile attacks the carbon bearing the leaving group from behind the leaving group, so 180 degrees from the carbon leaving group bond. As you can see here in this scheme, we have a methoxide anion attacking the carbon with the bromine leaving to form our product. Now, the solvents that are best for SN2 reactions are polar aprotic solvents, and this is because if we have a polar protic solvent, there could be hydrogen bonding between the solvent and the nucleophile, and this could prevent our nucleophile from being able to react with our substrate, and we don't want that. Now, the substrates that are best for SN2 reactions are primary carbons, followed by secondary carbons, followed by tertiary carbons. And this is because the nucleophile needs to attack the substrate 180 degrees from the leaving group, right? So it has to get in close proximity with that carbon in order to donate electron density. And primary substrates are the least hindered. Well, actually, methyl substrates are, but we're not going to talk about that. So primary substrates are the least hindered. So with primary substrates, it's easy for the nucleophile to get close to that carbon. But tertiary substrates are the most hindered. So there's a lot of stuff in the way. And there's not as much space for that nucleophile to get in close with that carbon. We could see that here in the bottom right hand corner. We have a carbon, tertiary carbon, a lot of bulky groups on it, not much space, so that nucleophile is going to have a lot of a hard time getting to that carbon. Now, for the experiment today, the first part of the experiment, we're just going to be making T-amyl chloride from T-amyl alcohol. And as we see here, the hydrochloric acid actually both provides a proton to protonate the OH group into water to make it a good leaving group, and it provides the nucleophile, the CO minus nucleophile. This portion of the experiment is straightforward. They get an extraction funnel, they add some T-amyl alcohol, they then add some concentrated hydrochloric acid, they shake it for a few minutes, and the reaction is relatively quick. And once they shake it for a few minutes, they're going to separate out the organic layer. They dry it with some drying agent and then pour it into a round bottom flask in order to perform a simple distillation to purify the product. And this is important because, like I've said before, it's rare that a reaction produces a single product. And in this case, there's a chance that there could be some elimination reaction occurring. on this substrate specifically. So once they do the simple distillation, they collect the pure distillate and they weigh the product to find the percent yield. Now, in part 2 of the experiment, they compared different types of alkyl halide substrates, 5 different ones to be exact, for both SN1 and SN2 reactions. Now, for part A, when they cover SN1 reactions, what we expect to be the best substrate, the most reactive substrate in this reaction, is T-butyl chloride, because it is a tertiary alkyl halide, which means it makes a tertiary carbocation, which is the most stable carbocation intermediate. This will be followed by allyl chloride. Even though it's a primary alkyl halide, its carbocation is stabilized through resonance. So it's the second most reactive, followed by sec-butyl chloride, and finally followed by both N-butyl chloride and N-butyl bromide. These are both primary alkyl halides, and they make primary carbocation intermediates, which are the least stable, so they will be the least reactive. Now, if we look over at part B for SN2, we expect the most reactive substrate to be primary alkyl halides, and if you look at the substrates, we have 3 of them. We have allyl chloride, N-butyl bromide, and N-butyl chloride. So these are going to be the most reactive substrates for SN2, theoretically. And the reason I have N-butyl bromide being more reactive than allyl chloride and N-butyl chloride is because bromine is a larger atom, so it's a better leaving group. It has larger orbitals. So when it takes the electrons, it's able to accommodate them better. They're able to spread out more, reducing electron repulsion, making it a more stable leaving group. Now, after N-butyl bromide, we have allyl chloride and N-butyl chloride being the next most reactive. Sec-butyl chloride is the third most reactive, and finally T-butyl chloride is the least reactive because it is a tertiary alkyl halide. It's got a lot of bulky groups surrounding it, making it really hard for our nucleophile to get into close proximity with that carbon bearing the leaving group in order to donate its electron density. And that's it, guys. Like I said before, the guy who made the video for this lab in particular did a really good job explaining the experiment and what happens and interpreting the results. So just watch it. He also provides all the data. But if you have any questions, feel free to email me.